Alright, so in this video we're just looking at the solutions to section 8.1 describing rotational motion. Number 74 asks, a steering wheel is rotated through 128 degrees as shown in the figure. Its radius is 22 centimeters. How far would a point on the steering wheel's edge move? So we have the steering wheel here, and it's being rotated through this 128 degree angle here, and we know that the radius length is 22 centimeters. So we know that the distance, the linear distance, is going to be given by the radius times the angle theta. So in this case we're looking at that distance. We know the radius is 22 centimeters. 22 centimeters is equivalent to 0.22 meters. Not necessarily required in this problem because you'll get the distance in the same unit as your radius, but that's just a habit I myself like to get into, is converting everything to meters. So 0.22 meters times an angle of 128 degrees, we have to know how many radians that is, or else we'll have the strange unit of degree meters, whereas remember radians is not a unit, so it's a ratio. So to convert 128 degrees into radians, we have to know that there are 2 pi radians for every 360 degrees. Or we could simplify that and say there's pi radians in 180 degrees. So let's make a conversion factor here where we have pi radians in 180 degrees. Cancel out our degrees. Then we take 128 times pi divided by 180, and we get 2.23 radians. So that's what I'm going to plug in for theta. And then when I multiply that by 0.22 meters, I get a distance of 0.49 meters, or if you prefer, 49 centimeters. And the next question, number 75, asks us, a propeller spins at 188 revolutions per minute. So there we have an angular velocity. Revolutions per minute is 1880. What is its angular velocity? That's the first thing we want to find. What is its angular velocity in terms of rads per second, radians per second? So this is just a conversion. We have 1880 revolutions per minute. We know that there's 60 seconds in a minute, so let's get that into seconds by putting a minute on top and 60 seconds on the bottom. And then let's convert revolutions into radians. We know that in one revolution there are 2 pi radians. So we'll just go ahead and cross out our revolutions. We end up getting 1880 divided by 60 times that by 2 pi. We should get 197 radians per second. Part B then asks, what's the angular displacement of the propeller in 2.50 seconds? And remember how angular displacement and angular velocity are related. Angular velocity is simply angular displacement over time. So if we know that the time is 2.50 seconds, let's just go ahead and rearrange that equation, and we'll get delta theta equals omega times time, which would then be 197 radians per second times 2.50 seconds to give us an answer in radians. We should get 492 radians. And again, radians not a unit, but we just want to kind of include it there to know what our number is referring to. Alright, so then number 76 asks us, the propeller in the previous problem slows from 475 revolutions per minute to 187 revolutions per minute in 4 seconds. What is its angular acceleration? So we know that it starts at 475 revolutions per minute, and it slows down to 187 revolutions per minute in the time frame of 4 seconds. Our equation for angular acceleration in terms of those variables is our change in angular velocity over time. Since our units are in seconds for time and minutes for our angular velocities, we're going to need to convert one or the other. I'm just going to convert everything into the standard units. So let's take this 475 and this 187. Let's multiply by 1 minute over 60 seconds. In other words, dividing by 60. So divide this one by 60 as well. And we'll also take 2 pi radians over 1 revolution. So in other words, multiplying both of those by 2 pi. When I run through all those conversions, I should get 49.7 radians per second for my initial velocity and 20.6 radians per second for my final angular velocity. The change in those, it goes from, we go our final minus initial, which is 20.6 minus 49.7. As it's slowing down, it should be a negative number there over 4 seconds. Finally, we're going to get negative 29 over 4, which is negative 7.27 radians per second squared. Finally, we're looking at number 80. This one is asking, a laboratory ultracentrifuge is designed to produce a centripetal acceleration of, I'm sorry, that's a centripetal acceleration is going to be just A, not alpha. Remember, alpha is angular acceleration. Centripetal acceleration is 0.35 times 10 to the 6th g. In other words, about 10,000 times, in the range of 10,000 times the rate of gravity. We're going to change that to 0.35 times 10 to the 6th times 9.8 meters per second squared, and that's going to end up being 3.43 times 10 to the 6th power meters per second squared. So that's our centripetal acceleration, and we know that that's happening at a distance 2.50 centimeters from the axis. So in other words, our radius is 2.50 centimeters. Let's get it in the same unit as our acceleration, which would be 0.025 meters. Now this equation we're going to use sort of is contrived from the fact that the centripetal the centripetal force ends up being our net force. We know that net force is the mass times the acceleration, and we know that centripetal force is mv squared over r. So in order to make this work, we don't have the mass, but thankfully when we set those two equal to one another, our masses cancel out, and we recall that A is v squared over r, which is actually an expression we already knew. But just to kind of remind you that centripetal force is the net force. So then another thing we know is that linear velocity is the radius times the angular velocity. So what we can do is we can put this in for our v and end up with r omega squared over r. And since we have two r's on top and one r on the bottom, we can cross one of these out and cross one of the r's on top out. We end up with r omega squared, which is an expression you can count on whenever your centripetal force is equal to the net force. You can know that your linear acceleration is related to your radius times your angular velocity squared. So our acceleration is 0.0250 times omega squared, and we actually know the acceleration, so let's put in our 3.43 times 10 to the 6th in here. So then we divide that number by 0.0250, and we get a omega squared equal to 1.372 times 10 to the 8th. And then when we take the square root of that, we're going to get omega is equal to, with our sig figs, we would say 2 sig figs, so it looks like 12,000 radians per second. So as you can see, a big angular velocity, but then again, this centrifuge is whirling around really fast, accelerating these things at 10,000 times the rate of gravity. So those are what we did with our 8.1 describing rotational motion problems.